So this is our by shift resistor. Okay, so depends on M bit. I can write when M is equals to 1. When M equals to 1, it would perform right shift operation, and G1 and G2 gate will initiate to provide input to G1 A and BFF. And when we have M equals to 0, when M bit is 0, M equals to 0, left shift happen and gate 3 and gate 4 gate 3 and gate 4 will work. Understand, you have to just describe these two things. M logic. If M is 1, right shift will be there. See, it is not fixed that M is equals to 1, so right shift happen only. But it is depends. If I have connected this with a positive bar, then M1, it will work at M1. But if I have connect this like over here, you can see I have connected this with negative line. Here it is connected with negative line. So 4 will work when M equals to 0. Over here you can say this G3 is connected with negative line. So it will work at complemented line. So it will work at M equals to 0. And for this case right shift, this G1 is connected with M and G2 is also connected with M. So right shift happen when there is M equals to 1. Understand? You can have screenshot of this. This is our by shift resistor. So rather than by shift, you can go for load shift because we can avoid this extra part to draw. Okay. Now let us move on counters quickly because it is taking too long. Counter. So first asynchronous counter. So in asynchronous counter, it is also known as a ripple counter. One to another. It is sending data from one to next one. So it is known as a ripple counter. So what is one bit counter? One bit counter, or sorry, not one bit. One. Do you need to count one? No. If we have more than one entity, 2, 3, 4, then we can count it. Otherwise, one is a single entity. We don't need a counter to count one value. So 2-bit counter or modulo, not 2-bit, but it is modulo counter of 2 or modulo 2 counter. So if it is counter, we have to convert the numbers or modulo numbers into the bits. Okay, we have given something, so I have to write 2 raised to something equals to 2 numbers. Modulo in the sense 2 numbers. So 2 raised to what should be there? 2 raised to k. 2 raised to k is equals to 2. 2 raised to k is equals to k. So what should be there? If 2 raised to k equals to 2, so what is value of k? So k is equals to 1. Understand? K is equals to 1. That is number of flip-flop requires. Okay, so 2 raised to 1 equals to 2. So k is equals to 1. So we require 1 flip-flop to make a modulo 2, or it is known as a binary counter. So here first we have to provide the input. Input is nothing but voltage. Okay, and we don't need to complement over here because we are intentionally going for toggle operation. Here we have clock and it is age trigger as well as negative clock. Negative age trigger clocks. Okay, here we have to compulsorily write this is VCC, voltage VCC. This is clock, CLK clock. And here we will have our output. Okay, so this is binary counter. And here rather than Q, we have to write we intentionally want to have toggle stage. This is K and here it is A bar. So this is one beat counter. Okay, what are the synonym for this are modulo 2 is one beat counter or it is binary counter. For 2 to 3 marks it may ask you. This is one beat asynchronous binary or ripple counter. Understand? Is it easy? In register we have to provide input beats as input. Okay, there were message beat as input. Here we have voltage as input. Okay, in previous case clocks were common. Now we don't have common clocks. It is asynchronous, so one by one clocks would be transferred. Okay, have a screenshot of this. Now we are moving towards the 2-bit. 2-bit in the sense, suppose I want to draw 4 modulo 4. Modulo 4 counter. So what should be there? 2 raised to k equals to 4. Okay. 2 in power of k should be 4. So here k is equals to 2. If it is counter, say generally it is not given in terms of 2 raised to n power. So we have to find out. If it is given clearly that draw for 2-bit counter, then it would be very easy, but they are not writing like this. They will ask for modulo 4 counter. So as k is equals to 2 is nothing but number of FF flip-flop. So we have to draw 2 flip-flop over here. Okay, so here we have to draw one output terminals. And this input is going to next as output. Sorry, clock. The output would be clock to the next one. Okay, this is very important thing to discuss. Here this output of A flip-flop is clock for next flip-flop. Okay, and here we have applied a common input to all. Understand? So here we have to write QA and QB. Now it is very important. If you learn this, then you can easily draw your truth table. Okay, it's very easy now. But you should understand this is terminal A and this one is terminal output for B. Okay, and how we will write our truth table? In truth table, we have to follow the scenario. A is LSB and B is MSB. Okay, so over here we can write this is A, this particular is A, and here it is B. Understand? And here it would digits what we generate. Okay, so always first is 0, 1, 0, 1. It is 0, 1. Okay, and the next bit would always 0, 0, 1, 1. Okay, we will go to the required number. Okay, here we want only 4 numbers, so this would be enough. So what would be the combination of 2? 2 0 would always 2 0 0 is binary of 0. Then 1 0. Excuse me. 0 1 is 1. Then 1 0 is binary of 2 and 1 1 is binary of 3. Okay, we are not going to discuss that, but this way we would have our output. And again, if I'm talking about this, then it would be again 0, and here it would be again 0. So 0 0 would be again 0. Okay, so this way we have to go for more and more. Suppose it is modulo 4. Suppose I'm asking for modulo 4. If it is modulo 4, so ripple counters are very easy. If it is modulo 4, then we have to find out the modulo 8, then we have to find out k value first. So how many 2, how many raised to 2 would be equals to 8. Okay, so here it would be k value, and we will have k is equals to 3. Okay, so we have to just draw one more flip-flop over here. There would be one more flip-flop. Okay, and here we have output of 8. We have to deal with the third output, and here it would be the QC, and this input would be extended. Here we have input to all. Okay, and output of previous would be clock to the next one, and it is again age triggered clocks, negative age trigger. Okay, so this is our modulo 8. You should come to know this thing. Okay, and for this, over here we have to draw C line. Okay, here it would be C. So C is 4 zeros, 1, 2, 3, and 4. 4 zeros and 4 ones. Understand? And we have to extend all the input up to 8 digits. Okay, because we want 0 to 8 as our output. Understand? If it is modulo 16, then or it is modulo 16 is known as a hex counter. So it would be 0 to 7 is octal. So modulo 16 is hex counter, and we have to draw one more flip-flop over here. 2 raised to 4 equals to 16. So it is nothing but counter of 16. Okay. And let us have one example for clocks. Quickly draw a clock. So how would be it? See here, for drawing a clock, I have to draw a single line. Then we are interested to draw okay, it should be at the equal distance. So now here we have a clock pulse over here. This is my clock. So it is negative age trigger, so we have to choose the downward arrow. And we just need to toggle value by 0 to 1 and 1 to 0. Understand? So here output for A is, say, this. So at this I can say we can extend this value over here. Okay. So here our input would be, say it was 0. So from this line now it is 1. From this it would be 1 to the next clock it will toggle. Then from another it would be 1. Then from next it would be 0. Then next it would be 1. Okay, kind of thing. So here this is our clock. This particular is output of A, and now we are interested in output of B. So for B, which is our clock, this negative or down arrow is our clock. So we have to react whenever we have down or downward arrows. Okay, so B would be 0 first, and from this clock it would be, you should manage the size. Okay, you must have equal size of this. So here it is up to this it is 1, then it would be 0, then up to next it is 1. Okay, if I'm writing over here, so here it is 0, here it is 0, then it is 1, then it is 0, 1, 0, 1, 0, and again it is 1. Okay, what we have written in our truth table, 0 1 0 1 0 1, and same way we have to write over here, it is 0 0, then 1 1, 2 0, here it is 2 0, then 2 1, again it would be 0. Okay, and if it is about C, if we are talking about, or we are going to draw modulo 3, modulo 16, then it would be ABC 2 raised to 3, that is 8. So modulo 8. So we have to draw C output also over here, and say it is C for modulo 8. So here we can draw, for this particular we have clock at this downward arrow, this is our clock, and over here this particular is our clock. So from the beginning it would 0, it will 1 for this particular area. From this to this it is 1. Okay, so here we can write, this is, in the beginning it was 0, all 0, 4 0 0 0 0 and 0, then 4 ones. So we just write, we need to draw truth table according to our requirement. Understand? If it is 16, then it would be D. So there would be 8 0 and 8 ones. Okay, so clock pulse diagram in this is very easy in counter, ripple counter. Okay, so this is model for ripple counter. Understand? Now suppose these are the modulo 2 raised to n counters. We have talked about 2 raised to n or modulo n counter. So they are indirectly proportional to 2 raised to n values. Okay, we don't need to add or subtract. Suppose I want to make counter of 3. Counter of 3. Then what would be there? Or generally they have asked for counter of 10. So direct 3 to 5, we will switch on 10. So for counter of 3, we have to add one more mechanism over here. See, in counter of 3, I have to add mechanism over here. Let I draw this mechanism first. Here it would be added to all. One NAND gate is there. Okay. So it will make 0. This figure would be 0. Okay. So first we have to make connections. Which connection? See, this line is connected over here and this particular value is clear bit. Okay. And the outputs are connected to this. This is connected to this. This output is connected to this and this is also connected to this. 3, 1 are connected. Binary 1, 1, 1. All are 1. So NAND gate says if there is 0, output is, if any is 0, output is 1. So no 1 is here, so output is 0. All ones. See, we have all 1 over here. 1, 1 and 1. All ones are there. No inverter is applied. So if all ones are there, this output would be 0. So there would be set clear bit. CLR. Clear bit would be active. Here we have clear bit. Preset clear bit. Okay. So it will make it 0. Clear bit. So it will convert whatever output we have into the 0. Okay. This is 3-digit output. So whenever there are 000, in this particular I'm trying to add it. Forget. So here it would be 0011. So suppose whenever we have mechanism like this, 111, say 1, and here it is also 1. All are 1, so it will set it 0. Okay, so this is counter of whenever all 1 with 2 raised to 3, that is 8. So this is counter of 7. Counter of 7 will count 0 to 6, right? So whenever we have 7 number, it will make it 0. Understand? Whenever we have 7 counter, this phenomena will go for counter 7. This is counter of 7. So if it has to count 0 to 6, okay? If 7, then it would equals to 0. If we have 7 number, then it has to convert to 0. So for 7, we have to draw counter of 8 first. Okay. We have to compulsorily draw counter of 8 and then counter of 8, we will use 7 numbers, 0 to 6 number only. And the last digit, 8th digit would be 0. 8 in the sense 7 is our last digit, 0 to 7 is equals to 8 count. So here 2 raised to 3 equals to 8. So all 3 would give us the 7 value. So here I can write it is 7 equals to 0. Okay, 7 becomes 0. So it will count 1 to 2, 6, and whenever there is 7, so it will make it 0. Then again it will count 1 to 6, and if it is 7, then it will make 0. Okay. If it is counter of 10, say decade counter of 10. So we have to use 4 input first. Okay. See, the mechanism would be the same. We required 4 counter of 10 would be 4. 2 raised to 10 equals to 2 raised to 4 equals to 16. So we have to go for counter of 16, and through this 16 we will use 10 digits only, 0 to 9. Okay, so first we have to draw over here counter of 4. 4 bits should be there, and then we have to connect them with the NAND gate. Okay, and what would be this NAND gate, specific NAND gate? I'm describing you again. Please rejoin.